everyone, my name is Svetunkov. I am Marketing Director of the Center for Marketing Analytics and Forecasting, and I am also a lecturer of Marketing Analytics in the Management Science Department of Lancaster University. Today we'll be talking about forecast evaluation and moving closer to the action, so we will discuss how to evaluate it for the point forecasts. In the previous video, we discussed the general principles and we discussed this forecast evaluation diamond, trying to understand why you would want to evaluate, what you would want to evaluate, where and how. And we stopped at how, because how, as I said, is a big topic. So we are moving to the next part of it. What is forecast error? This is the first question we want to discuss. In this plot that you see, we have a time series. The black line is the actual values, the purple line is the fitted, and the blue line is the point forecast that we get from the model. And the error is just the difference between the black line and the blue line when we talk about the test set. I will focus today's talk on the test set based evaluation. So we take the difference between the two. Mathematically, it's represented using this formula, E equals Y minus Y hat. The indices there show where we are and how far we want to evaluate the error measure. And we get our errors, like the difference, as I said, using these distances from the actuals to the forecasts. As simple as that, right? You've done that. What do we do? What do we have? Typically, when we get these forecast errors, we should actually keep in mind that they are not the same as the noise from your model or your residuals from your model. They are a different thing. Just as a reminder, as we discussed in one of the previous videos, any data has some structure and noise. Any actual observation is roughly just a combination of the two. If we do not capture the structure correctly, then we have, based on our estimated applied model, we have a wrong structure, we have specification error, and we have some noise. And in real life, we never know what the true model is. As the result, we will inevitably have the wrong structure and specification error. And when we take the difference between actual and the structure, in this case wrong structure, we get a combination of noise and the specification error. And this happens especially when we produce several steps ahead forecasts, because between now and, let's say, 6 weeks ahead, many things will happen, and most probably your level of sales will change somehow. So we will probably miss some information. That's why they are not the same thing, and that's why the forecast error should never be equal to 0. There are some very weird situations in practice when it might get to 0, but in these cases we're typically talking about very special products that is, for example, sold in fixed quantities every period. There is no forecasting task there. It's just, using the number in order to decide how many to stock for the next periods. So we get our forecast error. We know that it's never 0, and we want to somehow use it to evaluate the performance of our model. Each individual error only tells about performance on that specific observation, but we want to understand how model performed overall. So we need somehow to have overall measures, and these overall measures can happen in 2 dimensions. They can be related to bias and related to accuracy. Bias means the direction of error, whether it's consistently positive, let's say, or consistently negative, while accuracy refers to the magnitude of the error, of the size, general size of the error. And there is this classical plot that you see right now, which has low variance, high variance, low bias, and high bias, and you have 4 situations here. The ideal method should have low bias and low variance, but that does not always happen in practice. This relates to bias-variance trade-off, which we might discuss at some point in the future. This situation with low bias and low variance corresponds to all the points being very close to each other right at the center of the aim. The high variance means that there is a spread and we do not hit the same target, but we are hitting just around the main area. When it comes to high bias but low variance, you can see that the points lie outside. They are not in the center. So we see that there is a systematic issue here. If we consider the shooting example, you're shooting too high and too to the left instead of getting closer to the center. And then the situation when you have high bias, high variance corresponds to shooting higher than needed and also having a big spread of points. So I think that this image sort of covers or explains what bias is and what accuracy is. But what are they in terms of our forecast errors? So bias is typically measured using something called mean error. And the idea here is straightforward, I would say. You collect all the errors that you had and you take the arithmetic mean, the average. This is the mathematical formula of this. I'm not going to spend too much time on that. E here is the error, and we sum it up from 1 to h, where h is your forecast horizon. So in general, this mean error shows whether we tend to over-forecast or under-forecast. If it is positive, then we under-forecast, and if it is negative, then we over-forecast. Sometimes it is slightly counterintuitive. That's why people, in some cases, revert the sign and calculate minus e. But we are not doing that here. Ideally, this should be as close to 0 as possible, because if it is close to 0, then this means we have unbiased forecasts, meaning that the positive errors are cancelled out by the negative ones. There are actually papers showing that bias is somehow related to inventory performance. There is a relation. So if you have a very high bias, then your inventory costs will be higher as well. We typically do not find this sort of relation between accuracy and inventory performance. That's why it is important to track bias. It is in general important to track it so that you understand how your model performs, but as you see, it also aligns to your inventory decisions. And here are 3 plots, examples of 3 situations. In the first one, the mean error is 149.9, and it is a positive value. So it means that we are overshooting. You can see that the red line, the forecast, is above the blue line consistently. Now the second one, the mean error is 0.1. It is not equal to 0, but it is pretty close to it, so it's actually good. And in the third one, we have minus 150.1, and the line goes below the actual values, lots of them at least. And judging by the bias, we would say that the first and the third one are not very good, and the second one is good. You see, this error measure combines our understanding of the problem that the model should go through the series somehow with the specific error measure. Right. So this is good, but this shows you only bias, and positive errors will cancel out the negative ones. So how do we actually get rid of sign in order to understand what is the variability, what is the accuracy of our model? There are several methods. The simple and basic one, take absolute values. And based on that, we can propose, or we have mean absolute error, which is calculated as mean of all absolute errors, just exactly what it says. This is a fine measure used in many contexts. It is robust to outliers. Why? Because if you have a very high error, then it's not, expanded, increased. It's just a part of your cocktail, let's say. This error measure is minimized by median values, and it's proper for the median demand if you really want to work with one. Now, this is one option. What is the other one? The other one is root mean squared error. We take squares of each of the errors, we sum them up, we average them out, and then we take the square root. The square root here is important because it allows us to get back to the original units of the series. Because if you had oranges in errors, you square oranges, you have squared oranges in the summation sign, and you need to take square root to get back to the oranges, right? Okay, so that's RMSSE, root mean squared error. It is unfortunately sensitive to outliers. So if you have a big value, let's say all your errors were around 10 units, and then all of a sudden you had 100, then squaring it will expand the error measure, right? Because instead of 100, now we have 10,000. So it is sensitive to these situations, but it is actually proper for the mean demand. So if your model produces mean forecasts, if you work with mean forecasts, then this thing will measure your mean forecasts, and it is minimized by mean. And then there is also the slightly exotic one, which sometimes is also used in practice. It's called root mean squared logarithmic error. The idea here is it's very similar to RMSE, but we take logarithm of actual and logarithm of the predicted value. And then when we do the calculations, in the end, we take the exponent to get back to the original units. So this measure, not as sensitive to outliers as RMSE, but not as robust as mean absolute error. And it is robust for positive data only, and forecasts need to be positive as well. So if you have zeros in the data, don't even think of using this one, because logarithm of 0 is minus infinity. But it is minimized by something called geometric mean. So we have these three things, and I decided to show you a graphical example. So in this situation, I've generated data from something like log normal distribution. You see it has a long tail. And I calculated root mean squared error, mean absolute error, and root mean squared logarithmic error for mean, median, and geometric mean from this data. These are the values that you can see. The red line is the mean. Because of the long tail, it is stretched towards 0.5. When we use median, you can see that it is closer to 0. And then when we use geometric, it is even closer. And from this table that we see here, we can see the exactly thing that I've just mentioned. The RMSE is minimal when we use mean, right? It is the red color in this small table that I have. Mean absolute error is minimized when we use median. It's 0.23. And finally, the last measure, root mean squared logarithmic error, is minimized when you use geometric mean. This is just an example of what happens when you use that. So you need to be aware when you produce forecasts that you should actually align those forecasts with the error measures that you use. If you, for example, produce mean forecasts from your model and then you use mean absolute error to evaluate that, then you won't get the good understanding of the problem, because the model that is closer to the median will win, not the one that is closer to your mean demand. Right, so that's the property we need to keep in mind. And there is also a related question. What happens if we have, for example, more than 50% of zeros in the data? And that happens very often in practice when we talk about supply chain forecasting and retail forecasting. We're talking now about intermittent demand. We're not discussing that just yet, but it is important to mention it, because in intermittent demand, you can easily have the situation when you do not sell product in the majority of days, and then occasionally you sell it. If you have more than 50% of zeros, your median will be 0. So you need to be very careful with the error measure that you use, because as we discussed, mean absolute error is minimized by median. So it will tell you that the best forecast in this situation is 0 forecast. But this is not useful for decisions. What's the point in saying that, oh, we will not sell anything anyway, so let's not stock? No, that doesn't help in practice. We need to have something to make decisions. Furthermore, root mean squared logarithmic error will just break, because as I said, it doesn't work with zeros. And as I said, mean absolute error will prefer zeros. So the only measure you can use in this situation is root mean squared error. At least if you're interested in point forecast performance, then this is the thing that you would want to have. Also, a small lesson from this: if you deal with intermittent demand, just for sort of a sake, just as a sanity check, also include 0 forecast in your comparison. Because if you see that 0 forecast is winning, then something is wrong with your error measure. We should not do that. Okay, so mean absolute error, root mean squared error, and root mean squared logarithmic error are scale dependent. They have units, they have oranges inside them, right? But if we want to apply a forecasting method across different products, across different time series, we might want to know how it performed not only for oranges, but also for apples, for bananas, and so on and so forth. So we need to be able to somehow aggregate those values. How do we do that? If we want to see how model performs, you need to scale these error measures. And the modern approach is you take that error measure and you divide it by some statistics from the in-sample. It is actually quite important to say that we divide by in-sample and not the holdout value, so not the future actual value, because in the latter case, your final error measure will highly depend on it. And if your actual value was very high, you will probably deflate your error measure. So we have split into train set and test set, as we discussed in the previous video, and we calculate something based on our training set, and we use that to scale our error measures. Here are some examples. The first one is scaled mean absolute error, also known in practice as weighted MAPE. The idea is that you take mean absolute error from your method for your specific time series, and you divide it by the in-sample mean of the data. It's actually a fine error measure. It can be modified also to have root mean squared error in the numerator, and then we will have scaled RMSSE. They both are relatively easy to interpret, because roughly the interpretation is that you deal with percentage error, or some sort of averaged percentage error. But it might have some trouble on intermittent demand, because if your in-sample mean is lower than 1, then you're dividing by something lower than 1. As the result, your measure becomes very high. It's not a big issue, but this is something you need to be aware of. And also, if you have trends in your data and you do evaluation using rolling origin, once again, something we discussed in the previous video, then this might break as well, because it assumes that the mean in sample stays the same, that it does not change substantially. So there are issues with these error measures, but there are also some benefits that they have. To resolve the issues, we have something called mean absolute scaled error, where we take the same mean absolute error and divide it now by something much more difficult to understand, which is the mean absolute differences of the time series. There is another interpretation that it's not just mean absolute differences, that this is the mean error of the naive in sample, but that doesn't help in the interpretation, unfortunately. So the only way we can look at it, meaningful way, is that we take mean absolute error and just scale it somehow by something that is fixed. Because you see, if we say that there is a trend, if you take differences of that time series, then we no longer have an increase. We have a more or less stable time series. And so this means that you divide mean absolute error by something more or less stable, and it will not change much from one sample to another. It can be also modified for mean squared error. And there is a paper by George Athanasopoulos and Nikos Kourenzis who introduced that recently. And it is a fine error measure, but the problem of both of them is actually they are hard to interpret. So if you get the number, for example, 1.3, it doesn't mean much. It just means that you scaled it by something and that you received this number. But it works fine on any data. You can use it for any time series. And in case of intermittent demand, it should work fine as well. Now, we're moving a bit fast from one measure to another, but there is one specific thing we need to stop on and discuss in more detail. It's percentage errors. There is MAPE, mean absolute percentage error. The idea is you take the error from your forecasts, you take absolute values and divide each one of them by respective actual value, and then average things out. And there is also symmetric, so-called symmetric MAPE, which is not actually symmetric, which in the denominator sort of has average between actual and the forecast. That's why we have 2 appearing somewhere in the formula. Both of them have serious issues and should be avoided. I cannot stress that as much as I would want to do that. They should be avoided because they have some issues. And let's have a look what those issues are. There is a story of Siegfried and Roy, both imaginary demand planners. And they have very challenging tasks. Siegfried has this time series that goes down, so negative trend, and Roy has similar time series. And they both do actually pretty bad job trying to predict this time series. You can see the series goes down and they are saying that, you know what, our forecast will be flat and it goes like this. So what is the MAPE for both of these situations? For Siegfried, mean absolute percentage error was 0.1%. For Roy, it was 575.3%. So if we just look at these error measures, we would say that Roy needs to be fired because he's not doing a good job, and Siegfried probably should have a bonus for his brilliant job. But this would be a wrong conclusion, right? Why do we get this conclusion? Because we use percentage errors. Because Roy's data, as you can see, has units. And at the very end, those units are pretty close to zero. As the result, we are dividing by very small numbers, and our MAPE explodes and becomes very, very big. And in case of Siegfried, he's lucky because he's working with thousands of units. And as the result, his error measure is low. So you see how sensitive it is to the scale that you have. It's not very good characteristic, unfortunately. Now, one might think that symmetric MAPE is actually better because it somehow takes the average of those two things, forecast and actuals. The fact is, it's not. And here is another example. They had another two-time series. Well, actually, they had exactly the same time series, but Siegfried consistently over-forecasted it and produced slightly ridiculous forecast saying that we will have 1,500 units instead of 1,000, while Roy under-forecasted and said that we will have 500 units. So they did equally bad job, both of them. But what does symmetric MAPE tell us? It tells us that Siegfried had an error of 40.1%, while Roy had 66.6%. Once again, on the grounds of this measure, we would be inclined to say that Siegfried is doing better than Roy, but that's not true, right? That's just because of the error measure that we use. And actually, this is the property of the both measures. It's just the scale that impacts the value. And a couple more things. MAPE, mean absolute percentage error, prefers when you slightly under forecast. So if you have over forecast and under forecast, the under forecast would be better in terms of MAPE, while symmetric MAPE prefers when you over forecast. So it's the other way around. So they are not very good in terms of assessing the performance of models. Furthermore, if you have 0 in your actual values, then MAPE becomes infinite because dividing by 0 gives you infinity, while symmetric MAPE becomes 2. And 2 is a good number, but it does not tell you what's happening in reality, in real world. So these are already bad things, as you can see, but in order to make things even worse, they are not minimized by any known statistics. You remember a few slides ago, we've discussed that mean absolute error is minimized by median, RMSSE is minimized by mean. We have no idea what MAPE and sMAPE are minimized by. Well, actually, that's not entirely true, because Stefan Kolasa has showed in one of his papers that MAPE, under some very special conditions, is minimized by mode, but you really need to meet those special conditions. So in real life, that's not very, very often met, does not happen very often. So conclusion from this is that the percentage errors should be avoided. It's just the formulation of those errors that makes them distort the reality, distort the message that you have. If possible, if you cannot avoid those error measures, then use MAPE. At least it has the clear interpretation that this is the percentage error, while in case of symmetric MAPE, you're dividing by this average, and which complicates the interpretation. Okay. Now, the related issue to this, should you set targets based on error measures? And I know that some companies do that. They say to their demand planners that your demand needs to have error measure of less than 15% or something like that. Well, the answer is no. because your error measures can be anything. As we've just seen, for one person it was 500, for the other it was 0.1. So there's no point in setting the threshold. And MAPE of 10% does not mean a good performance on its own. Actually, on its own, any error measure does not mean anything. Mean absolute scaled error of 0.98 does not mean much either. The interpretation there is too complicated, so I'm not going to explain what it might mean. So how can we tell whether the model did well or poorly? Well, we cannot. But what we can do instead, we can compare the performance of our model with other models. And here we come to the state-of-the-art approach in forecasting. You calculate the chosen error measure for different models, and then you select the best one based on that error measure. You can even have all of that in one number based on the idea of the relative measures. We just take our measure from one model and divide it by the measure of another model. If it is greater than 1, then the first one has the higher error than the second one. This means that the second model does better. If the final value is lower than 1, then it is the other way around. Your first model is doing better than the second one. We can actually even define specific measures. For example, there is relative RMSSE, where you take RMSSE from one model for this specific time series divided by the other, and you kill two birds with one stone. First, you do the direct comparison, and second, you get rid of the units. So now you can take these error measures and aggregate them across several time series. This also aligns, there's the third bit, it also aligns with the so-called forecast value edit by Mike Gilliland, and the idea that you're trying to see how much value your forecast brings in comparison with a simple benchmark. So you can, for example, calculate naive, the performance of naive method on your data, and you can say by how many percent your method is better than naive. You can also use global mean or any other benchmark depending on situation. It might be a different thing. Now we're moving to the last bit related to the accuracy, which is the one number measure. If you really need to have one number that tells you this is how our model performs across different time series, then you can use mean, median, geometric mean, or anything else. But you should keep in mind that this is just the aggregation of the whole thing. When you just use one number, for example, mean of all mean absolute scaled errors, then you get a very averaged performance, right? And your model, it is like an average temperature in the hospital. Your model might do very well in the majority of time series and fail just on one of them. And because of that failure, your error measure will be higher than you would expect. So it gives you a general information, but you should keep in mind that you sort of lose some of the important elements in the statistics when you just use one number. Right. So concluding what we've discussed today, forecast errors are typically not zero. We discussed that there is structure and noise. At the very best, they reflect the noise of the data, but typically they also contain some information about the wrong specification. You can use mean error for bias just to see whether you under forecast or over forecast. Ideally, your bias should be zero, but that's not always achievable in practice. And one thing that I didn't mention, aggregating of mean error can also be done using scaling. You can use the same principles that we've just discussed on previous slides by dividing by mean in sample or the first differences and so on. When it comes to accuracy measures, you have several fundamental options. We can have root mean squared error, which is minimized by mean. We have mean absolute error, which is minimized by median, but you should not use it on intermittent demand, because as we've discussed, it prefers zero forecast in many cases. And then we have exotic one, root mean squared logarithmic error, which is minimized by geometric mean. It breaks when you have zeros or negative values. And finally, when you want to aggregate measures, you can use scaling by in-sample, scaling by differences, or you can calculate relative error measures just by dividing by benchmark. Also, important element, avoid percentage errors. And if you haven't heard me correctly, please avoid percentage errors. And seriously, do not use mean absolute percentage error, or do not use symmetric MAPE. There is no good reason for doing that anymore. We have other measures that actually do a much better job than these two. And don't forget that when you aggregate things, you end up with just number. It is sort of descriptive, but you're sort of ignoring the distribution. And we will discuss how to deal with the distribution in future videos. So this is it for this video. This is one of the videos in the series of educational videos from the Center for Marketing Analytics and Forecasting of Lancaster University. You can scan this QR code, or you can follow the link in the description of the video to see what services we provide. One of those is, for example, executive training, and we can help your demand planners do better in practice. So get in touch with us if you're interested, and don't forget to put thumbs up if you like this video. Thank you. Bye-bye.